Something that's kind of interesting about if you take an object and you submerge it in a liquid, well, here we've got an object and it's under some water, is the force that the pressure causes is always going to be perpendicular to the surface. So, because of pressure and I have some area, the force is always going to be perpendicular. So for this triangle, it's going to be right there. So the effects of water pressure, the force is going to act perpendicular to the surface. And I have a nice little demo on this, and I also talk about how depth is related to speed. So here I have my 3-holed jug, and I pull that off. You can see the water kind of spurting out. It's going to be spurting out perpendicularly to wherever I drilled those holes at. You can also see that the water coming out of the top hole is coming out slower than the middle hole and slower than the bottom hole. So pressure is related to how fast it comes out, and it comes out much faster at the bottom simply because there's more pressure to it. Now, one of the last things I want to mention is going to be something called a displacement rule. And if you take an object and you completely submerge it, then it's always going to displace a volume of a liquid equal to the volume of the object. And this can be a great way to measure the volume for irregularly shaped objects. I mean, if it was a cube, then sure, we could calculate it, length times width times height. If it was a sphere, sure, we could calculate it. There's a formula for that. But if you have this weird, funky, irregularly shaped rock, then it's kind of hard to measure. But if we know that the volume of the object is the same as the volume of the water, then that's kind of a powerful thing to know. So let's kind of move into this concept of buoyancy. And I'm probably not telling you anything that you don't already know. Now, we know that if you were to try to do some chin-ups, so you're kind of this block right here, and you were in air, then you could probably do what, 5, 10, 20 if you're strong. But if you were to hang off the edge of a diving board just like this, then you can do like a bazillion chin-ups. So kind of the reason for that is there's this thing called buoyancy in a liquid, and essentially if you had to lift yourself upwards with a force of, let's just say 1,000 newtons right here, when you're in the liquid's going to give you some buoyant force, so this F sub b, and so the force that you need to lift yourself up is going to be less than the 1,000 newtons. So if this buoyant force was, for the sake of argument, just 500 newtons, then your apparent weight to your arms is going to be smaller, so it's going to be like maybe 500 newtons. Now, this Greek fella by the name of Archimedes, he was the one that, kind of came up with a mathematical description of this, and essentially he related, this buoyant force, how much buoyancy, and what he said is that if you have an immersed body, so an object that's either partially or completely in the water, so you could have an object like this, or an object like this, it's going to be buoyed upwards by a force that's equal to the weight of the fluid that it displaces. So this guy right here is going to displace a lot of weight, so there's going to be a relatively large buoyant force. This guy right here is going to displace some water, maybe not nearly as much, and so the buoyant force is going to be a little bit smaller. But both of these guys are going to displace some weight in water, and that's going to be equal to the buoyant force. This is going to apply to both gases as well as liquids. So, kind of a conceptual example, also using apparent weight, is suppose you have this 3 kilogram block, and that's actually a mass, it's not a weight, but still, if you pop it on a scale, it's going to read 3, and if you had a puddle, or if you had a scale right next to it, and we're going to dip this thing in, and some water is going to pour out, initially this scale right over here is going to read 0. When we go ahead and we dunk this weight into the water right there, then we're going to read some apparent weight, and that apparent weight is going to be 1. How much water was displaced? Well, that's going to be 2 kilograms, because this guy right here reads 1. That guy right there is going to be essentially the rest of it. These two numbers have got to add up to the original weight, so it's going to be 3. So we've displaced 2 kilograms worth of water. So here I have a mass hanging from a force probe. You can see it's reading about 4.8 newtons, and I'm just going to dunk this down into the water. It's going to displace it. It's going to experience a buoyant force, and now you can kind of see that it's reading a force of 3.9. Now, you may be asking yourself, well, why do we have this thing called buoyancy? Well, we do know that pressure is going to depend on density, gravity, as well as depth or height, if you will. So, right here we're going to have some pressure on this object, and right down here we're at a larger depth, and so we're going to have more pressure. So the pressure on the bottom is going to be larger than the pressure on the top, and it's this pressure differential that's going to give rise to the buoyant force, and not surprisingly, it's going to be in the upwards direction. And one thing that's kind of interesting is as we go deeper and deeper and deeper, here we're going to have a larger pressure than right here. Right over here is going to be a much larger pressure than right here, and we're going to have the buoyant force, and it's actually going to be the same buoyant force because the pressure differential between the top and the bottom are the same. Now, how much is this buoyant force? Again, it's always going to be in the upwards direction. Well, the buoyant force is going to be equal to the weight of the fluid that it displaces. In this case, it's going to be water. And if you remember that weight is equal to mass times gravity, we can simply write the weight as such. And then we can say that the mass is going to be equal to the density multiplied by the volume. And so we can say that the buoyant force is going to be equal to the density of water multiplied by the volume of the object multiplied by gravity. Now, one thing to kind of keep in mind is, well, this is going to be a pretty important equation. We could say that the buoyant force is going to be equal to the density times the volume times gravity, kind of shorthand. And that's going to be a volume that is going to be taken up. So if you had an object that was sitting in water, maybe kind of as such, and if you dumped this object totally in the water, so if you put that object down there, then there's going to be a large buoyant force. If you put that object right there, so it doesn't displace all of the water, it's only going to be the volume that is submerged. So because this guy right here is a smaller volume submerged than this guy right there, the buoyant force is going to be smaller. So take a second and think about how you could increase the buoyant force on a submerged balloon. So I'll let you do that guy real quick. So there's my balloon, and we're going to submerge this thing into some fluid. And we know that the buoyant force is going to be equal to the density of the fluid multiplied by the volume that is submerged multiplied by gravity. Obviously, if we increase the volume, so as this guy gets larger, then the buoyant force is going to go up. We could also increase the density of the fluid, so as this guy goes up and that guy goes up. Increasing the density of the object is not going to do a darn thing about the buoyant force on it, because this is the density of the fluid, not of the object. Be very careful. So it's going to be both A and B. So this kind of answers the age-old question, why do people float in water? Well, let's go ahead and, how much buoyant force should we expect? If you Google the volume of a person, it's going to be about 0.1 meters. So the buoyant force is going to be the density of the fluid multiplied by the volume multiplied by the gravity, and for simplicity we'll say that the person is wholly submerged, and we just use the density of water, so it's going to be 1,000 kilograms per cubic meter multiplied by 0.1 multiplied by gravity, which is 10, and the buoyant force is going to be 1,000 newtons. Now, if you were to look at the weight of a person, say their mass multiplied by gravity, if you had 100 kilogram person and gravity would be 10, then their weight would be 1,000 newtons, and if we were to draw the forces on this guy, well, we would have the buoyant force upwards, which is going to be 1,000 newtons, and his weight is going to be acting downward, which is also going to be 1,000 newtons, and he's going to float on water. Now, some people, if you have a lot of muscle or something like that, then perhaps your mass might be larger, in which case you might not be able to float on water. But if you were to go to the Dead Sea, pretty much everyone can float on the Dead Sea, and you can repeat this calculation and you would come up with a buoyant force of 1250 newtons, essentially replacing that 1,000 with 1250, in which case 1250, and you would definitely be able to float on the Dead Sea because the buoyant force would be larger than your weight, and actually you wouldn't need to submerge all of your volume at that point. This also kind of explains why a ship might float at a certain height in water, but it would float higher in salt water because, in general, salt water has a larger density than water. So let's talk about when an object is going to sink or float in the language of the buoyant force, so this F sub b. An object's going to sink when its weight is larger than the buoyant force. it's neither going to sink nor float when the weight is equal to the buoyant force, and it's going to float when its weight is less than the buoyant force. And we could also talk about this in the language of densities. If the density of the object is larger than the density of the fluid, then it's going to sink. It's neither going to sink nor float when the density of the object is equal to the density of the fluid, and it's going to float when the density of the object is less than the density of the fluid. So here's kind of a tricky one. Give it a try and then let's talk about it. How many forces are acting on a submerged body at rest in a fluid? Well, we're always going to have the weight acting downwards, and it's submerged, so we know there's going to be a buoyant force on that. And so you might have been tempted to say 1 or none, but actually there's going to be 2. There's going to be buoyancy and the force due to gravity. So let's talk about flotation just a little bit more, and let's think about how we can have an object, say a steel ship, and if it was compressed into a little tiny block, then it might sink, but if we were to expand it out so it displaced a larger volume, then we can get a larger force. So if we had just a 1-ton brick by itself, maybe it's going to displace maybe an eighth of a ton, in which case the density of the object is larger than the density of the water, and it's going to sink. But if we took that same 1-ton block of iron and we shaped it into a bowl, then it can displace a larger volume of water, which means it can displace a larger weight of water, and it can have a larger buoyant force, and it's going to allow it to float. So you can kind of see that this guy right here is going to displace more volume, more water weight, and a larger buoyant force than this object right here. What this kind of boils down to is the buoyant force is going to be equal to the density of the fluid multiplied by the volume of the object multiplied by gravity. And kind of what we're doing is we're increasing the volume of the object when we go from this step to this step, and so we're increasing the buoyant force. Now, I know I mentioned this on an earlier slide, but I'll say it again, is the more dense of a fluid, it's going to be a larger buoyant force. Why? Well, the buoyant force is equal to be the density of the fluid, volume of the object, multiplied by gravity. And if we think about salt water versus fresh water, salt water has a larger density than fresh water. So as the density goes up, the buoyant force is going to go up, and a ship's going to float higher in salt water compared to fresh water. Now, an interesting application of this is as long as an object floats, it's going to displace its weight in water. So if we had some scale and it was reading maybe 3, and we dunked a cube in there, then it's going to displace its weight in water, and it's still going to be reading 3. As long as it floats. If we were to dunk like a piece of iron in here and it went down to the bottom, then obviously the scale is going to read harder. But as long as it floats, then the scale is going to read the same. And a real life application of this is going to be this wheel in Scotland. And essentially, if you take a look at this guy, then what it has is it's got a bucket over here and a bucket over here. And these guys are both filled to the brim with water. And so the weight over here is going to balance out the weight over here. And essentially, this guy is going to be lifting boats up from right here to right here. And we want to do this with as little, just as little power input as possible. Well, if you think about it, these guys are going to balance each other out. If we were to take a boat and we were to dunk this boat in here, so just like that, then some water is going to spill out, but these two guys are going to have the same weight. And in your mind's eye, as long as these two weigh the same, then it's not going to take a whole lot of power to turn this thing. So this wheel right here is actually an ingenious way to lift boats up using relatively little power.